Okay, here we go. This is the review for the final exam. This is part 1 of 3. So question 1, the activation energy required for a chemical reaction can be decreased by which of the following? So activation energy, every reaction has a progression. It moves along, and then in order for the reaction to get started, the reactants have to have enough energy to get up and over a certain height, a certain hill, which is the activation energy. And if that activation energy is high, the reaction goes more slowly because it takes more time and energy to get over that hill. But if you add a substance called a catalyst, it lowers the activation energy. Now it's much easier for the reaction to go ahead because the hill that the reactants have to get over to proceed is much lower. So the answer here is a catalyst. A catalyst is a substance that lowers the activation energy of a reaction without being consumed as part of the reaction. How many liters of 1 molar hydrochloric acid are required to neutralize exactly 2.5 liters of 3 molar NaOH? So there's a couple of ways to go about this. One is that you can calculate how many moles, if the NaOH is 3 molar, then that means that there are 3 moles in 1 liter of the NaOH. Well, we don't have 3 moles, we have 2.5 moles. Or sorry, 2.5 liters. So how many moles is that? Well, if you cross multiply, 3 times 2.5 is 7.5 moles. Well, 7.5 moles, if you have 1 molar hydrochloric acid solution, let's set that up. 1 molar hydrochloric acid solution means 1 mole in 1 liter. So how many liters would you need to have 7.5 moles? Well, the answer here is 7.5, right? 1 over 1. 1 over 1 is the same as 7.5 over 7.5. The other way you could have looked at this one is that the NaOH is 3 times as strong as the hydrochloric acid, which means you'd need 3 times as many liters. 3 times 2.5 is 7.5. Either way, this way will always work if you set up the proportions like this, even if the numbers aren't sort of round, clean numbers like they are here. So this is the way I would suggest that you do it. Set up a proportion, find out how many moles you need to neutralize, and then figure out what volume of the other solution you'd need to neutralize that many moles. Which of these reactions represents neutralization? Okay, neutralization is what happens when you mix an acid and a base. You get 2 products every single time. Acid and base produce salt plus water, always. The salt here is a general term. It doesn't just mean what we think of as salt, which is sodium chloride. It could be any metal, non-metal combination. But the key here to look for is, does it produce water? Well, the only one of these choices that has water in it is choice B. Right? That's the only one that has water as a product. So that right there tells you that this is a neutralization reaction and all the other ones couldn't be, because it has to have water as one of its products. Which of these samples is a solution? Okay, remember, a solution has to have 2 parts. It has to have a solvent, which is water most of the time, but it can be other things. It also has to have a solute, which is something dissolved in it. So that means that a pure compound is not a solution. A solution is a type of mixture. So when you look at these abbreviations here, S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous. Well, solid water, which is ice, is not a solution. It's water. Liquid water, same thing. Liquid water is just H2O. It's not a mixture of anything. It's just water. We're assuming it's pure here. And CO2 gas, well, that's just gas. It's not mixed with anything. The only one that's a mixture, according to the name here, aqueous means dissolved in water. So CO2 dissolved in water. Now you have a mixture of these 2 things, which we call a solution. Okay, with the boiling points of these four compounds, which has the strongest intermolecular forces? Simplest thing here is stronger intermolecular forces mean higher boiling point, because the intermolecular forces are holding the molecules together, right? They're drawn together, which means if you want to boil them and get them apart, that's harder to do because they're holding on to each other. So whichever one of the compounds has the highest boiling point, greater boiling point means stronger intermolecular forces, or IMFs. So in this case, the highest boiling point is 19.4 Celsius. So the strongest intermolecular forces would be with the hydrogen fluoride, or hydrofluoric acid. If we have 5 milliliters of a 0.2 molar HCl solution, how much do we need to neutralize 10 milliliters of NaOH? So this is similar to the problem we had a couple of problems ago, number 2. We need to figure out how many moles are we going to neutralize and how much is it going to take to do that. But this time we're working a little bit backwards because we're given how many milliliters of solution we needed to neutralize, how many milliliters were neutralized, and we want to know what's the concentration. So how many moles were neutralized? Well, how many moles were neutralized? It's 0.2 molar, which means moles per 1,000 milliliters, or per liter. How many moles were there in the 5 milliliters? Well, when we do that out, we find that that would give us 0.001 moles. That's how much hydrochloric acid we used. Well, if we used 0.001 moles of hydrochloric acid, that means that we neutralized 0.001 moles of sodium hydroxide, because they're canceling each other out, equal amounts. So now we can take the 0.001 moles of NaOH. If we know that we had 0.001 moles in the 10 milliliters, so we're setting up a second proportion here, just like we did with the other problem that we did like this. Well, how many moles are there in 1,000 milliliters, or 1 liter? When we do that math out, 0.001 divided by 10 times 1,000 is 0.1 moles per liter, or 0.1 molar, which is choice A in the answers. As an aqueous solution becomes more acidic, what happens to the hydroxide concentration? Well, remember the chart looks kind of like this. Neutral is in the middle, pH of 7. Stronger acids have more hydrogen, stronger bases have more hydroxide. So as we proceed, this is the acid side, this is the base side. As we go toward the acidic side, we can see here that the OH is going down. The OH gets less over here than it is over here. Okay, so as the solution becomes more acidic, the hydroxide concentration goes down. Okay, if we have this reaction here, what is water doing in this reaction? Remember, water is a compound that's called amphoteric, which means it can be an acid or a base. Well, an acid is something that gives up protons or hydrogen ions. A base is something that takes hydrogen ions in the Bronsted-Lowry definition, which is what we're looking at here. So what's happening to the water? Here's the water here, H2O, and then on this side we have OH. Right? If we rewrite H2O as HOH, and we turn that into OH, well, what's happened? Well, we've lost a hydrogen. So the water in this reaction has donated its hydrogen, which makes it an acid in this definition. Okay, and the ammonia, the NH3, is the base here. Okay, which which sample of NH3 in this set of choices will take the shape of and completely fill a 1,000 milliliter container. All right, so this is a question about the different states of matter: solids, liquids, gases, solutions. And here's what you need to remember. Solids have defined shape and volume. Okay, if you put a solid that's a cube into a round container, it doesn't suddenly turn round. And if the container is bigger than the solid doesn't get bigger. You can't take a solid and squeeze it into a smaller container. You can't make it smaller. The shape and the volume are fixed. It has to do with how the molecules or atoms are arranged. Liquids have no definite shape, but they do have a definite volume. Okay, if you take a half gallon of water and put it into a 1 gallon container, the water doesn't suddenly expand and fill up the 1 gallon container. Likewise, if you take a gallon of water and try to pour it into a half gallon container, you're going to spill half your water because you can't squeeze it into a smaller container. Gases do not have a definite shape or a definite volume. All right, you can compress gases, like the propane for grills and things like that, compressed air in scuba tanks or oxygen tanks in hospitals and things like that, CO2 tanks if you use welding equipment or whatever. Those are all gases that have been compressed into smaller containers. If you release or open those containers, the gas comes out and expands, so it can change its volume, and you can put it in a square container or a round container or whatever. It'll fit either way. So no definite shape, no definite volume. That's a gas. The pH of a solution changing from 5 to 3, what happens to the hydronium ion concentration? All right, so 2 parts to this. One, you have to recognize what's happening as the pH gets lower. Lower pH, okay, as the pH goes down, the hydrogen ion or hydronium ion concentration goes up. It kind of seems backwards, but that's just the way the scale works. Lower numbers mean more hydrogen ions. Okay, so that's the first thing. So we know it's going to be going up, so it's going to be a bigger number, so it's not going to be 1/100th, it's not going to be 1/10th. The hydrogen ion concentration is going up. So now the question is it 10 or 100 times bigger? Well, each step, okay, from 0 on up, each step on the scale in either direction, could be going that way or this way, each step on the scale represents a power of 10, because these are logarithms, they're exponents of 10. So if you go 1 step on the scale, that's times 10. If you go 2 steps on the scale, it's times 10 times 10, or 10 squared. 10 squared, of course, is 100, so that means that a difference from 5 to 3 is a change of 100 times. If you want another step, it'd be 1,000 times, and so on. So each time you move a step, you move a decimal place, basically. And you just have to remember that going down means more hydrogen, going up means less hydrogen. Which of these substances can act as an Arrhenius base in an aqueous solution? Well, Arrhenius definition means acid has hydrogen, base has hydroxide. The only one of these compounds that has any hydroxide in it is the lithium hydroxide. So that's the only one that could be an Arrhenius base. The other ones might be bases in a different definition, but Arrhenius is very specific. Hydrogen means acid, OH means base. Okay, so we have the solubility curve, and we want to see which of the substances given is most soluble, which means it could have the most dissolved, at 60 degrees Celsius. So the first thing we need to look at is 60 degrees. Okay, that's this line right here. So we're looking along that line. The other thing to look at is we're only looking at certain compounds, not everything on the chart. Because the one that would be the highest which is kind of hard to see, overall is the potassium iodide because it goes literally off the chart. Okay, and if we assume that that line keeps going up, it would be way higher than all the other ones. The next one is sodium nitrate, but that's not on our list. The next one down is potassium nitrate, but that's not on our list. The first one we come to that's actually on our choices is ammonium chloride. So that's the one that has the highest, and the point of that line that we're looking at is right here. Okay, that's the highest one up. The next one down is this one, and then this one, and then this one. But the highest one, which is what the question was asking, is the ammonium chloride. So that's choice D. Okay, another solubility question. Which of these solutions would be saturated at 30 Celsius? So again, if we go to the chart, we're looking at the line that is 30 degrees Celsius, and we're looking at KClO3, potassium chlorate, or sodium chloride. So those two lines would be these two lines. Okay, so that's what we're comparing to our answers. And the other thing that we need to know is that the chart is based on 100 grams of water. So the values that are on here are 100 grams. So some of these choices have 200 grams, which means it would be double whatever the chart says. So which one of these fits? Well, the first choice is 12 grams of calcium chloride per 100 grams of water. So that would be, if we look at the chart, and we look in here, and it's kind of hard to see, especially because I put these extra lines on there. If you look at the 30-degree line here, and you look at the calcium chlorate line here, you see that roughly the place where those two lines intersect is just a little higher than 10. Okay, so it would not be unreasonable to say 12 grams of potassium chlorate in 100 grams of water is saturated. The saturation point is where the two lines meet, right? The line of the compound versus the line of the temperature, and then you look across to see what the amount is. So the amount here was a little more than 10. 12 is a good enough estimate. 30 grams of NaCl, the line here is above the 30, so that's not accurate. And neither one of these is close. If you doubled the amounts or cut them in half, they would not fit. Which of these is formed by sharing electrons? Sharing electrons means it's a covalent compound. Okay, covalent compounds are always made of two non-metal elements. So basically two elements from that same area of the periodic table, which is top right. If you have a metal combined with a non-metal, then that is usually, most of the time, going to be an ionic compound. Okay, so two different types of compounds, covalent and ionic. The one that we're looking at sharing electrons is covalent, which means we need the compound that's two non-metals. Potassium is a metal, calcium is a metal, chromium is a metal. The only one that is two non-metals together is the carbon tetrachloride. A solution with a pH of 11 is tested with phenolphthalein and litmus paper. So which is the correct combination? So phenolphthalein, when we did the titration with the vinegar, we put those drops of stuff in there and it turned pink when the titration was over. That was called phenolphthalein. That's an indicator. And then litmus paper is another way to test for acids or bases. And you need to know that so for acids, the phenolphthalein, right, is clear, and the litmus is red. Okay, and for a base, the phenolphthalein is pink, and the litmus is blue. Okay, so it's going to be one of these combinations depending on whether it's an acid or a base. So now we need to figure out how, is it an acid or a base? Well, the pH of 11. Okay, acids, if we're talking about pH, acids have a pH less than 7, bases have a pH greater than 7. So since 11 is greater than 7, it means we're looking at a base, which means the phenolphthalein should be pink and the litmus should be blue. So that's choice C. All right, so you need to know two things basically for this question. What does the pH number tell you? Bigger than 7 is base, lower than 7 is acid. 7 exactly would be neutral. And then you need to know how the different indicators react. The two that we've dealt with are phenolphthalein and litmus paper. Phenolphthalein is clear in acid, pink in base. Litmus paper is red in acid and blue in base. Which of these produces hydrogen ions in aqueous solution? Well, the way to tell this, hydrogen ions in solution means acid, first of all. Okay, that's really by both the two definitions we went over, the Arrhenius and the Bronsted-Lowry. So it has to have hydrogen, which rules that out. And then the other thing to look at is, where is the hydrogen in the formula? Most of the time, something that's going to be an acid is going to have the hydrogen at the front. Okay, hydrobromic acid. OH here, OH is indicative of a base, so we could have crossed that one out. And then ammonia NH3, the H is at the end, so that's not an acid. So HBr, hydrobromic acid, is the choice there.